Welcome to our deep dive. We are thrilled to have you joining us for a specially curated study session today.
Yeah, absolutely. If you're, gearing up to take the Ethical Hacker Pro certification, you are in exactly the right place.
Right. And our mission today is to decode a fantastic stack of source materials we've been provided, specifically a highly detailed slide deck titled SQL Injection Heist and its accompanying quiz content.
Think of this deep dive as your ultimate guide to understanding how digital bank robbers operate behind the scenes, and more importantly, how to architect defenses that actually stop them.
Okay, let's unpack this. Using a heist analogy is a highly effective framework to map out complex cybersecurity concepts so they stick.
The mechanics of a database breach can feel, well, they can feel really abstract, especially when you're just staring at lines of query syntax.
Yeah.
But when you map it onto the physical steps of casing a joint, bypassing security, and emptying a vault, the architecture makes logical sense.
Yeah, we aren't just memorizing definitions here. We are analyzing the attack vectors so you can anticipate the adversary.
Scott?
So, to set the baseline, let's look at slide 1, Anatomy of a Digital Heist, Mastering SQL Injections.
This slide kicks off our Ethical Hacker Pro certification prep by highlighting a pretty stubborn reality. Despite being a known vulnerability for decades, SQL injections remain among the most powerful and complicated attacks out there.
Right. They are responsible for catastrophic internet breaches involving stolen credentials, financial records, and massive intellectual property dumps.
And the reason they persist is that modern infrastructure relies so heavily on databases communicating dynamically with web front ends. If that communication channel isn't sanitized perfectly,
The system is completely vulnerable.
exactly, it's the big leagues of cybercrime because the payoff is the entire back-end data store.
Which means we need to deeply understand the layout of the target network. Moving to slide 2. Casing the target architecture. The sources provide a really clear three-part analogy for the infrastructure here.
Yeah, let's break that down. First, you have the web server. Think of the web server as the delivery driver. They handle the TCP/IP connections, moving the HTTP requests and responses back and forth across the internet.
Second, you have the web application. This is the receptionist. The application layer takes the user input, interprets what is being asked, and formulates the query.
And finally, you have the database itself. This is the locked vault storing the actual loot.
And this brings up a critical exam trap highlighted in the quiz source.
Oh, absolutely.
Yeah.
You have to memorize where the actual flaw resides. The vulnerability in a SQL injection attack lies strictly in the web application.
Not the database.
Emphatically no. It's not the database, not the file system, and not the web server. The database is simply a machine executing the SQL queries it receives. It's the receptionist, the web application, that is being manipulated into passing a forged, malicious query into the vault.
That distinction is paramount for your certification, which leads directly into our first interactive study prompt. Listeners, we want you to pause and answer this with a 2 to 3 sentence response. Ready? Based on the roles of the server, application, and database, why is the web application the most logical point of exploitation rather than attacking the database directly?
If you look at the broader network topology, the answer really is access. The database is typically isolated deep within a private network, shielded by multiple firewalls, intrusion prevention systems, and strict routing rules.
You just can't easily reach it from the outside.
Right. The web application, however, is public-facing by design. It's built to accept input from external unverified users on the internet. It's the one door that must remain open for the business to function, making it the optimal vector for delivering a malicious payload.
To understand how that payload is constructed, next up, slide 3, the master key, weaponizing syntax.
This slide focuses on two seemingly minor pieces of punctuation that fundamentally alter how a system processes data.
The single quote and the double dash.
Yes. In SQL syntax, the single quote acts as the pivot point. It signals to the backend interpreter that the normal data string has ended and a new system command is beginning.
And the double dash serves an equally destructive purpose. In SQL, a double dash indicates that the current line of code is ending, and anything following it should be treated as a comment.
And because comments are designed purely as notes for human developers, the SQL engine completely ignores them during execution.
So by appending a double dash, the attacker effectively truncates the backend logic.
Exactly. The database completely drops whatever validation sequence was supposed to happen next, like verifying if a password actually matches the username provided.
They're essentially turning the application's native parsing rules against the database. The system believes it's simply executing legitimate instructions passed down by the application layer.
totally unaware that the input string was weaponized to alter the query's underlying logic. That is the core mechanism of the exploit. The database engine cannot distinguish between the developer's intended query structure and the attacker's injected commands.
Understanding the mechanism naturally leads us to the objective. Let's turn to slide 4. Motives for the heist. The sources categorize 5 primary goals for these attacks.
First is bypassing authentication, which we just outlined. That's logging in as an administrator without needing the password.
Second is information disclosure, where the attacker extracts sensitive data. Third is remote code execution, which elevates the attack to running underlying operating system commands on the host server.
Fourth is compromising data availability, which involves deleting logs, wiping tables, or dropping entire databases. And fifth is compromising data integrity, which means altering the stored data or defacing web pages.
There is a massive exam trap here regarding the CIA triad, confidentiality, integrity, and availability.
Yes, examiners routinely test whether you can distinguish between an attack on availability versus integrity. If a hacker alters a database to change product prices or defaces a web page by inserting their own content, they have compromised data integrity.
It's highly common for students to incorrectly choose data availability in those scenarios. Availability refers to destroying or blocking access to the data, like ransomware or a dilution command. Integrity refers to unauthorized modifications that change the truthfulness of the data.
Which brings us to our second interactive study prompt. Think through the cascading effects of these motives. If an attacker alters a database to change product prices, which specific motive does this fulfill, and what is the potential cascading impact on the business?
Modifying prices leaves the data fully accessible, meaning availability is intact, but the data is no longer accurate.
That is a textbook compromise of data integrity. The cascading impact could involve massive financial losses through artificially discounted transactions, severe reputational damage, and a complete loss of customer trust once the manipulation is discovered.
Now that the motives are clear, the sources lay out the tactical execution. Onward to slide 5, the master plan, phases 1 and 2.
Phase 1 is information gathering. Before launching a full assault, attackers probe the system to map its architecture. They intentionally submit malformed queries to force the application to throw an error message.
And if the application is poorly configured, these error messages will reveal verbose back-end details, like the specific database version or table structures. The sources also highlight the use of the union operator during this phase.
The union operator is critical for extracting data. In SQL, union is used to combine the result sets of 2 or more queries into a single output. For an attacker, this means they can append their own query, say, asking for the user credentials table to the application's legitimate query.
As long as they match the number of columns and compatible data types of the original query, the database will return both the expected data and the stolen data seamlessly to the web page.
Phase 2 focuses on testing for vulnerabilities. The slide contrasts function testing with static and dynamic testing.
Function testing is essentially rattling the doorknobs. You append a single quote to a URL parameter and observe if the site throws a SQL syntax error.
Right, whereas static testing involves analyzing the actual source code offline, scanning for improper input handling. Dynamic testing, on the other hand, evaluates the application while it's running, monitoring how it interacts with a database in real time under various load conditions.
Once the vulnerabilities are mapped, the attacker moves to execution. Let's look at slide 6, phase 3, launching the attack, the interrogation.
The sources divide attacks into 2 main categories based on how the data is retrieved. First is in-band SQL injection, which is the most straightforward. The attacker uses the exact same communication channel to inject the malicious code and gather the extracted results.
Error-based and union-based injections are classified as in-band. The second category is blind or inferential SQL injection.
Blind SQL is fascinating because the application is configured to suppress database errors, meaning the attacker doesn't get a visible readout of the data they are querying. Instead, they have to infer the data by asking the database a series of true or false questions.
The sources specify 2 types of blind SQL. Content-based, where the query alters the HTTP response slightly depending on whether a statement is true, and time-based, where the attacker uses commands like wait for delay to force the database to pause for a few seconds before responding if a statement is true.
The exam cheat code provided in the sources is highly specific regarding this methodology. If a certification question describes an attack methodology that resembles playing 20 questions with the server.
Asking if the first letter of a password is A, then B, and measuring the response.
Exactly. The answer is launching a SQL attack, and specifically they are describing blind SQL. It requires thousands of tedious requests, but it is highly effective for extracting data when direct output is blocked.
The ultimate goal of this extraction brings us to our next point. Now for the big one, slide 7, phase 4, emptying the vault.
This covers advanced SQL injection techniques. It starts with enumeration, which involves systematically mapping out the user privileges, schema, and back-end infrastructure.
Then comes password grabbing, directly targeting credential tables.
If the database service account has excessive privileges, attackers can achieve OS interaction, allowing them to read and write system files directly on the host server. And finally, the most severe outcome, complete transfer.
Complete transfer is the ultimate failure of access control. The source material highlights the open row set function.
Yes. In SQL Server, Open Row Set is a command designed to allow ad hoc distributed queries to remote data sources. If an attacker can inject this command, they can instruct your database server to establish an outbound connection to an external attacker-controlled database.
They essentially build a shadow pipeline, replicate your entire table structure, and pipe the entire vault's contents out of the network in one fell swoop.
That level of compromise requires immediate detection, which brings up our third interactive study prompt. Imagine you detect open row set commands originating from your web application layer. Construct a brief incident response hypothesis explaining what phase of the attack is occurring and what the attacker's ultimate goal is.
If you see open row set traffic that wasn't explicitly authorized by a database administrator, you are dealing with phase 4, advanced SQL injection.
The attacker has moved far past reconnaissance and vulnerability testing. Their ultimate goal is the complete exfiltration of your entire dataset to an offsite location. Your incident response must focus on immediately severing that outbound connection and identifying how the application layer allowed that command to reach the database.
To execute these phases at scale, attackers rely on automation. Let's check out the gear on slide 8, the burglar's tool belt.
The slide lists several frameworks. BSequel Hacker is an automated all-purpose injection framework. Havige is a well-known tool used to automate database fingerprinting, retrieve password hashes, and access the underlying file system.
Marathon Tool is specialized for executing the heavy, repetitive queries required for time-based blind SQL attacks, and Droid Stickly is utilized for testing vulnerabilities specifically from Android operating systems.
For certification purposes, you must link specific tools to their use cases. The key association to memorize here is SQL Power Injector. If an exam scenario asks for the specific application used to find and exploit SQL injections directly on a web page, the correct answer is SQL Power Injector.
The sources also provide a vital bonus summary comparing two defense tools, IBM Security App Scan and Dot Defender. Understanding the functional difference between these two is critical for network defense architecture.
IBM Security App Scan is a comprehensive dynamic application security testing, or DAST, solution. It assesses overall application security and manages risk for both mobile and web environments by scanning for vulnerabilities during the development or deployment lifecycle.
And Dot Defender, conversely, is an operational defense mechanism. It's a web application firewall that works in tandem with an intrusion prevention system. It actively sits in line, examining HTTP and HTTPS traffic in real time to detect and block malicious SQL injection payloads as they are transmitted.
However, attackers are constantly developing methods to bypass those inline defenses. We explore these evasion tactics on slide 9.
Moving to slide 9, dodging the security cameras. The primary objective when evading an intrusion detection system is to manipulate the input string so it executes successfully in the database, but no longer matches the known attack signatures the IDS is programmed to recognize.
The sources outline several techniques, and we have some simple analogies to clarify how they confuse signature detection. Let's start with character encoding.
Character encoding involves replacing standard ASCII characters with their encoded equivalents, such as using the SHAR function.
The analogy here is communicating via a phonetic alphabet. If a security system is strictly scanning for the word DROP, it might completely miss the payload if the attacker transmits Delta Romeo Oscar Papa. The security scanner fails to recognize the signature, but once the payload reaches the database engine, it decodes the phonetic instructions and executes the dropping AND.
The second technique is manipulating whitespace. Instead of a standard query, the attacker inserts excessive or irregular spaces between SQL keywords.
You can think of this as adding long, awkward pauses between words in a spoken sentence. An automated voice recognition system representing the IDS might fail to register the phrase because the timing and structure don't match its baseline expectations.
However, the database backend acts like a human listener. It ignores the awkward pauses, focuses on the core words, and pieces the executable command back together.
The third evasion method involves inline comments, where the attacker breaks up SQL keywords by inserting comment brackets directly inside the word itself.
This is analogous to whispering random nonsense syllables right in the middle of a command. The signature-based scanner gets confused by the extra noise and allows the traffic through.
But the SQL database is explicitly programmed to strip away anything designated as a comment. It removes the whispers, concatenates the remaining fragments, and executes the reconstructed malicious command.
There is a significant trap alert regarding evasion terminology on the exam. If you are presented with a definition stating that the code was modified to be hard to read and understand, the specific term the exam requires is obfuscated codes.
Do not select character encoding for that specific definition, as obfuscation is the broader concept of intentionally masking the code's intent. Precision in terminology is what separates a passing score from a failing one on these professional exams.
Moving from evasion to mitigation, time to play defense with slide 10, fortifying the vault, countermeasures.
The foundational principle here is the principle of least privilege. Database server accounts must run with minimal rights. You should always use lower privileged accounts for standard application connectivity.
A web application should never log into the database using SA or administrative credentials. Furthermore, default error messaging must be disabled or customized to prevent the application from leaking architectural blueprints to attackers during the reconnaissance phase.
To ground this in a historical context for your exam, the material references the 2011 Sony hack, where over 1 million accounts were compromised through a massive SQL injection vulnerability.
The critical takeaway for your certification is that this breach could have been prevented by proper configuration and rigorous front-end penetration testing. It was not a failure of network layer encryption or port filtering, but a failure to sanitize input at the application layer.
Which brings us to the ultimate defense mechanism outlined on slide 11.
Slide 11. The ultimate lock. Server-side data validation. Client-side validation is easily bypassed, therefore validation must occur on the server. The sources structure this into 3 distinct non-negotiable layers. The first layer is input size limits.
By enforcing strict length constraints, such as limiting a U.S. zip code field to exactly 5 characters, you physically deprive the attacker of the space required to inject a lengthy executable command string.
The second layer is data type enforcement. The application must accept only the explicitly expected values. If a field requires an age, the system must enforce a strict integer-only check, completely rejecting any alphabetic characters or symbols.
The third and arguably most critical layer is binary input rejection. The system must actively filter out and reject malicious syntax.
Regarding binary input rejection, there is a specific phrasing you must commit to memory for the quiz. Memorize this exact sentence. Decline any entry that includes binary input, comment characters, or escape sequences. Recognizing that specific criteria is essential.
Let's solidify this concept with our fourth and final interactive study prompt. How does separating input validation into size limits, type enforcement, and character rejection create a layered defense strategy against SQL injection?
The concept here is defense in depth. By decoupling these checks, you create overlapping security controls.
Right. If an attacker successfully bypasses character rejection using advanced encoding techniques, their payload will likely trigger the size limit threshold because encoded strings are inherently longer.
And if they manage to keep the payload short, they will still fail the data type enforcement because their query requires characters, while the application strictly demands integers.
You are forcing the attacker to navigate a multi-layered gauntlet rather than a single locked door. That is the essence of secure architecture. Relying on a single point of validation is a guaranteed path to compromise.
As we near the end of the material, watch your step on slide 12. Distractor Hall of Fame. Don't click these. The quiz source contains several intentional traps designed to test your actual comprehension versus mere memorization. Let's break down why these incorrect answers are wrong.
Trap 1 claims the flaw is in the database. We have established thoroughly that the vulnerability exists within the web application's failure to sanitize input.
Trap 2 suggests you should block ports 161 and 162 to stop SQL injections.
Ports 161 and 162 are dedicated to SNMP, the Simple Network Management Protocol. While blocking them prevents SNMP exploitation and network reconnaissance, it does absolutely nothing to prevent Layer 7 web application attacks like SQL injections, which travel over standard web ports like 80 or 443.
Trap 3 advises using a VPN to stop SQL injections.
The virtual private network provides an encrypted tunnel for data in transit, which is excellent for defending against wireless attacks like WPA2 cracking. However, a VPN does not inspect the contents of the payload. An attacker can send a perfectly encrypted malicious SQL command right through the VPN tunnel into your web application.
Finally, Trap 4 suggests scanning the OS for bugs to stop SQL injection.
OS patching is critical for preventing an attacker from escalating privileges once they are already inside the system, but it will not prevent the initial SQL injection vulnerability, which resides in the application's code, not the operating system's kernel.
Let's synthesize everything we've covered. Let's review Slide 13 and Slide 14, the Exam Hacker Cheat Sheet Parts 1 and 2. To succeed on the Ethical Hacker Pro certification, you must rapidly associate the concepts.
Let's do a rapid-fire review.
Yeah.
Single quotes, pivot the syntax. Double dashes truncate the back-end logic by creating comments.
Altering database records or defacing pages is a compromise of data integrity. Deleting records impacts data availability.
If a scenario describes an attacker playing 20 questions with server response times, they are executing blind SQL.
For tools, SQL Power Injector targets web pages, while Marathon Tool automates time-based blind attacks. Evasion techniques that render code hard to read involve obfuscated codes.
And ultimately, proper server-side validation requires declining binary input, comments, and escape sequences. Mastering these associations ensures you aren't just guessing on the exam, you are structurally analyzing the questions.
Finally, Slide 15. Mission brief complete. You now possess a comprehensive understanding of the digital heist architecture. You recognize the tools, understand the mechanics of the evasion techniques, and have the blueprints to avoid the exam's most common distractors.
You are thoroughly prepared to tackle the SQL injection domains of the Ethical Hacker Pro certification. As you move forward, I encourage you to apply this technical knowledge to your daily digital interactions.
Every time you authenticate into a web application, your banking portal, your corporate email, or a retail site,
That exact architecture of the delivery driver, the receptionist, and the vault is operating silently in the background. Recognizing how fragile that transaction can be without rigorous validation provides a profound appreciation for why defense in depth is so critical to our modern infrastructure.
it fundamentally changes your perspective on web architecture. Before we conclude, we want to leave you with a provocative thought to consider as you continue your studies. Consider how the rapid evolution of artificial intelligence might change the landscape of blind SQL injections.
If an attacker's script no longer has to manually play a tedious game of 20 questions, but can use AI to predict and automate the true-false queries instantly,
How will our defense tools like Dot Defender need to evolve to catch a threat that moves at the speed of thought?
the arms race of cybersecurity never stalls. The methodologies simply grow more sophisticated on both sides of the vault.
Keep studying, keep questioning the architecture, and keep diving deep. We will see you on the next deep dive.